single phase full bridge inverter with RL load. So this is my single phase full bridge inverter with RL load, or also called as a square wave inverter. Here we have a input DC supply, and we have 4 IGBTs in the form of switches. So in our case we will be using a power BJT along with this anti-parallel diodes, and the load is RL load. So let us start simulating the circuit in in eSim. So we have the eSim window. We click on the new project, and we can call it as full underscore bridge. See to it that no spaces are left in between, because the spaces are not allowed. Full bridge inverter RL load. Alright, so I'll click on OK, and next I'll click on open schematic. It will ask for creation of a new schematic, so you can click on yes. Okay, alright. So here is my workspace in my eSIM, and here I will be adding all the components one by one. So yeah, let us begin now. So I'll go to place component, and the first component which I want to place is the DC source. So I'll type capital DC, and I place the source over here. Alright. Next I want to add BJTs. So I'll click over here, I'll type eSim underscore NPN. eSim underscore NPN will add NPN transistor. So here I will be adding it over here. I'll require 4. So one over here. Then other one, I'll place it over here. Similarly, I'll require 2 more. So one I'll place it over here. I'll orient it as per the requirement later, but first let me add the 4 BJTs. Alright. To give a trigger pulse, the trigger pulse at the base. So this I will orient it in a different way. So like this. Right click, orient, and mirror. Alright. I'll require anti-parallel diodes also. So I'll click over here, and I'll type eSim underscore diode. So here I'll have add 4 diodes. I'll orient them later. These anti-parallel diodes will allow the current flow in the reverse direction also. And in eSIM we have in the form of eSIM diodes. Now I'll quickly orient them. Right click, orient clockwise. Oh, anti-clockwise I should have oriented. Counterclockwise. Yeah. The similar thing I will be doing for all the diodes. Counterclockwise. And lastly for this also. Alright. Now I will be requiring a load, RL load. So again I'll go over here, and I'll type eSIM underscore R. So this is the register in eSIM. So I'll place the components over here. Then I'll also require an inductor. So eSIM underscore L. I'll add the inductor over here. Alright. So now is the time to connect them together. So I'll connect them quickly with a wire. Alright. So this way I'll be connecting the negative supply to the emitter terminal of BJT. Here also I will be connecting the emitter terminal, and then lastly I will make the connections for the anti-parallel diodes. Okay, so all the connections have been done. Now for the load, I'll connect the load. Alright, and now the anti-parallel diode. So in this way I'll complete the entire connections. Okay, see to it that wherever you place a connection there is a small junction formed, right? This green color dot which you see over here. So see to it that the connections are proper, or else later in the simulations you will find yourself into trouble. Alright, now I will require to plot various voltages, right? So let's say I want to, and also, oh, I forgot. So we will have to add a ground also. So here I'll right click. Okay, it is in the wire mode only. I'll select place component and I click over here and I'll type eSim underscore ground. I have to place the ground over here and then connect it with a wire. Okay, so most of the connections are over and now we will have to add the plots, various plots we will be having, right? Before that, let's enter the value of resistor. So the value of resistor will be right click over here, edit value. We'll give the value of resistor as 10 ohms. I'll click on OK and I'll just go back, right click on the for the change of value in the inductor. So inductor value we are selecting it as 10 millihenry. 10 millihenry. Okay, all right. So the value of R and L is already been given, and now we have to give the trigger pulses also. So let me go to place component. Okay, yeah. So here I will add pulse. In under eSIM sources you will have pulse. So here else I'll be adding 4 pulses. Pulse source, one over here. Um, then next one will be over here. Then below also for these two transistors also will require pulse. One over here again and the last one over here. Okay, so opposite transistors, in this case this transistor and this transistor will require the same triggering pulse, and this transistor and this transistor will require the same triggering pulse. Let them connect, let us connect them with the wire. So here is the wire, let me connect it. All right, and the other terminal will go to the emitter. So here I will be connecting it to the emitter. All right, here also I'll do this connections. Okay, below also here it will go to the base terminal and other one will be going to the ground, because ground and emitter are connected for these two transistors. Alright, so the pulse connections have been made, and now I will be adding the global label. So here I want to plot input, so I'll type over here in, orientation will be right, input is selected, so here is the input, in. I'll connect it with a wire quickly. Okay, next I will be adding plot, because I want to view the input voltage also. So I'll add one plot over here. So very quickly we have added the plot. Alright. Now for the output also we will be observing the plot. Alright. So here I will be naming it as, let me add the global variable, global label, and call it as output 1. Alright. I'll place it as output, and orientation will be left or right, no problem. Here it is. And one more one, global variable, output 2, I'll place it over here, because we want the voltage across the load, so it will be out 1 minus out 2, that will give us the voltage across the load. Now I want to add the plot. Okay, I'll go to place component and add plot on both the sides. Here is the one, and other one I will add over here. Here it is. Join them with the wire. Here also I'll connect them with the wire. Okay, all right. Also, I need to add, need to plot the current flowing through the load. So for the current flowing through the load, I'll have to delete this wire and shift this a little bit that side. Okay, I delete this wire as well, and now I will be adding plot. Under eSim plot, I'll select plot I2. So this will help me to plot the current. So now I'll join them with a wire. Alright, so the schematic is mostly complete. Alright, so here we'll have a DC source, the 4 BJTs along with the anti-parallel diode and RL load. Now after that, save the schematic. Click on the annotate schematic button and click on annotate. Click on OK. So it will give the name, right? Here it is given the pulse V2. Here it is given V5, V4 and V3. Alright. Um, okay. Next is we have to generate the netlist. Click on netlist. Go to Spice. Check the default format and click on generate. So it will generate the netlist of the schematic. Save the netlist. So it will save the netlist. Alright. Again you can save the schematic. Now we have to set the parameters. So I'll go back to the eSIM main window, and now I'll click on Keycad to NGSpice button. Here I have to give the details, the source details. So here I'll give it as start time as 0. Then step time I can give it as around 500 microseconds, and the stop time will be around 50 milliseconds. Alright, these are the transient analysis parameters. Then the source details, the supply voltage I wish to give it as around 10. And the voltage source V2. Let us see what is the voltage source V2. So voltage source V2 is for transistor Q1. All right. This is Q1 and Q4. The transistor Q1 and Q4 will have the same triggering pulse. All right. So for V2, we'll be giving initial value as 0. Then the pulsed value will be 2.5 volt. Delay will be 0. Delay, I'll give it 0 right now. Rise time and fall time will be 1 nanosecond. Then the pulse width will be zero point 0.5 milliseconds and the period will be 1 millisecond. Alright, so I'll go to the next one, next source. Next source is V4. So V4 also we have to, V4 is this one. So V4 we have to give a delay of let's say 0.5 milliseconds, right? Because uh, these Q1 and Q4 should be turned on simultaneously, and Q3 and Q2 should be turned on simultaneously. They should not be turning on simultaneously. That is why we'll give a delay of zero point 0.5 millisecond. So your initial value will be 0, pulse value will be 2.5, then delay will be around zero point 0.5 milli, then the rise time will be 1 nano, fall time will be 1 nano, pulse width will be zero point 0.5 milli, and the period will be 1 millisecond. Again for V3, V3 will be same as V4. So here it will be 0, 2.5. Delay will be there because it is similar to V3. Then rise time, fall time 1 nano. Pulse width will be same for all. Alright. And the last source is V5. Now V5 is similar to V2 without any delay. So here I'll give it as 0, 2.5, 0, 1 nano rise time and fall time. Pulse width will be zero point 0.5 milli and 1 milli. Alright. So in this way, we are giving no delay for V2 and V5 pulses, and V3 and V4 pulses, we are giving a delay of zero point 0.5 millisecond. Remember, when you annotate uh, in your circuit, when you create this V2, V3 labeling might be different. Alright, because it depends upon which pulse source you have added first, and then accordingly it will annotate. We have to add the eSim model, transistor model for NPN transistor. So click on add. We'll go to the transistor and select NPN. Similarly, we will do it for all. Go to transistor, select NPN. We are selecting the library of NPN transistor. So we have to repeat this for 4 times. NPN. Alright. Then the 4 diodes will come. We have to add the diode model. So click on add, go to the diode and click on D. You can add Schottky also, no problem with that. Alright, we can either select Schottky diode or we can select simply D also. That will also actually do. So no problem, let us add the Schottky diode already. So let me add Schottky diode over here. Schottky diode and the normal diode in Schottky diode is a little faster. So it will respond to the changes, let's say in the frequency of the output a little faster, because in an inverter input is DC, right? And the output is having a frequency. So that's why it's better to add a Schottky diode. Okay. There are no sub-circuits. We have added all the device modeling. We have given the analysis and we have given the source details. So now is the time to click on the convert button. It has successfully converted your Keycad to NGSpice. Click on OK. So we'll go to the project and click on refresh. So it has added the library files npn and Schottky diode, and it has added all the project files. Now is the time to simulate the circuit. So go to click on the simulate button. It will take roughly 5 to 10 seconds to respond. Yeah. So it is giving us the output. So your U3, I of U3 is nothing but this is the U3, this is the current flowing through the RL load. So as we have seen in the theory, the current flowing through the RL load is a like a rising exponential and falling exponential. To expand this, you right click on your mouse and drag a rectangle. So here it is. As you can see, it's rising and falling. If I want to view it in more details, here it is. Rising exponential and falling exponential. That is what we have covered in the theory part. Here it is, output waveform. I mean, output current waveform looks like this, and it's exactly behaving the same manner. All right. So this is about the load current. Let us check about the output. Okay, it is showing you V out 2 and V out 1 separately, but we want to plot V out 1 minus V out 2. All right, so we have to do the changes. Also, I mean, this is my input 10-volt DC. Also, I want to make this background of this NGSpice as white background and this in blue color, right? So I'll do the following changes. I'll double click on cir.out file and I'll do some changes over here. So before the plot statements, you'll add the following lines. Set color 0 equal to white, then set color 1 equal to black, then set color 2 equal to blue. Also, we will increase the thickness of this waveform. So we will write a statement set x brush width equal to 3. All right. And also I want to plot the waveforms of you know output 1 and output 2 you know together, because output is waveform across the load is V out 1 minus V out 2. So I'll write over here plot V out of 1 comma V out of 2. That means it's plotting across the load. Alright, because here we have labeled output 1 and output 2. We want the voltage across the load. So we will be writing V out 1 minus V out 2. That is same as writing plot of V of out 1 comma out 2. Then we'll click on the save button, and this is the Python plot. Here also we can view the plots, right? So let me just plot it and show it to you. Yeah. So here also we can view the plot and save the plot over here. But still, let's run this, simulate this again. All right. So it's giving us the value across the load. So let me the RL load single phase full wave bridge inverter, voltage source inverters these are, and it's exactly matching with what we have covered in the theory. All right. Now the voltage across the load. So voltage across the load is should be a square wave. All right. So here it is. The voltage across the load is coming out to be a square wave. Let me expand it a little further. So here it is. All right. It's exactly here also it's behaving the same way. It's a square wave. It will generate a square wave output. All right. And if we view it along with the, let me show it to you. Yeah, here it is. So this waveform and this waveform, if you view it together, this is what we have and done the analysis for. So output of a full single phase full wave bridge inverter is a square wave, right? And the current flowing is a rising and a falling exponential waveform. So in this way you will simulate your circuit, and you can save your plots. Input waveform is a DC. Let me show it to you. Yeah. So input is a DC, output is a AC waveform. It's in the form of a square wave which will have a frequency, right? You can calculate the frequency from here. You can calculate the one period, and 1 divided by that period will be the frequency. Similarly, you can also calculate the frequency from the waveform over here at the output current waveform. All right. So in this way, you can view, you can simulate a single phase full wave bridge inverter with RL load. All right. So yeah, so that is what we have to do, and we end the simulation over here. So yeah, eSim is an open source EDA tool for circuit design, simulation, analysis, and PCB design. So it's an integrated tool built with various open source software such as Keycad, NGSpice, GHDL, Verilator, MakerChip, and the new edition Skywater 130 PDK. Right, it is released under GNU General Public License. That means it's completely open source. And this tool was developed by eSim team at FOSSEE IIT Bombay. So I'll recommend and encourage most of the users to start using eSIM for circuit simulation and analysis. So yeah, thank you for joining. The